So I'm Claudia Diaz. I have two hats, as you can see in the slide. I am Chief Scientist at NIM Technologies, and I am also an Associate Professor at the University of Leuven, where I've worked for the last 20 years on designing and analyzing privacy technologies, and in particular, anonymous communication systems. So I will try in the next 20 minutes to share with you some of the insights and key points that I have learned doing this work. All right. So let's start from the beginning. What does it mean to be anonymous? So anonymous is a word that comes from Greek. It comes from the prefix an and the word onoma, and it means without a name. So to be anonymous is to be nameless. So basically, it means that we have some subject that to whom we cannot link or attach a name. Now, this subject, who is this subject? It can be anything. It can be somebody physically present, like I am present here. Maybe you don't know my name if I hadn't told it in the beginning. It can be the owner of a device, an account, or a wallet. It can be the person whose data record, for example, patient record is in a database. It can be the subject making a transaction, the writer of an online text, you name it. Okay. And what about this name? What do we think of names? So names are not just the name that is printed in your passport. That's one of your names, but there are many other identifiers that can function as your name. So for example, unique IDs, obviously, but also your cookie identifiers identify you and are your name towards a website that you have visited. The key to a database that has your records is the name where they can aggregate more data. Your IP address at the network layer is your name, all right? So what's in a name? It's not just why do we want to prevent naming this individual, because the name is not just the name. The name usually is connected to a history of other actions or activities that this person engaged with, okay? So together with this name, we will typically have a database of past actions that we can link to that name and therefore to the individual. So if we can name this person, we can also connect this person to a lot of other history about her, and then therefore learn potentially a lot of private information. Now, a final thing I want to say in this introductory slide is that when we think of knowing or not knowing the name in technical terms, is not usually about either I know it and I know everything, or I don't know it and I know nothing. The way we model anonymity in typically is that there is a bag of names and we don't know which one corresponds to the individual. So you should think about it like, for example, all the badges of the conference, all the participants. You see me, you don't know who I am, but you know I'm a participant in this conference. And in this table of badges, you might want to guess or try to find which one is mine. And maybe you have no clue about any tag can be equally likely to be mine, or maybe you can think, okay, well, she's a female, so probably it's a female name, and you know she looks like Southern European, so it's probably some names might be more likely than others. So this is the way we typically think about anonymity and naming when we are looking at online anonymity. Okay, so what about anonymous online activity? We have a user, Alice. She wants to access some service and she wants to do it anonymously, meaning that at the site of the service, it should not be possible to know what her name is. Now, if we want to model anonymity in a classical secure communication model, we would have something like this. We would have Alice talks to Bob, she sends a message to Bob, and we have an adversary, Eve, that can look at the communication, and a secure channel would provide confidentiality, authentication, and integrity for that message. Now, the problem with this model is that it doesn't have, we cannot model anonymity there because, as we can see, Alice sends a message to Bob. Therefore, Eve already knows who Alice is talking to, and she knows how to link the sender and receiver of the communication. So this is not a model that we can use for online anonymity. Instead, when we talk about anonymity, we typically think of something like this, which is that we have many Alices and many Bobs, and we can not tell which Alice is talking to which Bob. Again, the adversary also becomes a little bit more complicated because we don't have just a line from Alice to Bob. Now we have a complicated system. It could be the adversary is looking at Alice's communications. It could be that the adversary is looking at Bob. It could be that the adversary is looking at some pieces of the network, some intermediate entities, or it could be that the adversary is looking at the whole network. If your adversary is, for example, the NSA or some entity that has very broad visibility over internet communications. So the first really key point that I want you to take from here is that you cannot be anonymous on your own. In order to be anonymous, you have to be embedded or covered in a group of people, okay? You want this group of people to be diverse. This is very important. If you have, imagine that you're accessing information about cancer in a website and you don't want anybody to know that you're accessing this information. If you're using a system that many other people use to access information about cancer, then even if I cannot tell who you are, I can still infer a lot about the activity you're conducting, right? So you don't want to use a system that only other people who are doing similar things to what you're doing use it. You want to use a system that is used by a very broad and diverse base of people doing a very diverse set of things. And in this way, when I see you using this system, I have a lot of uncertainty about what you're actually doing, because you might be looking at a website, you might be sending a message, you might be just checking your Dropbox, you might be reading your email, you might be doing all kinds of things. So the more diverse the users of the network and of the system, the more anonymous you are. So anonymity loves company, and in order to be anonymous, you have to be, you have to work together with other people. This is a very important point. This is not the case if you just care about confidentiality. If you just care about confidentiality, for my own data, I generate a key, I encrypt my data. I don't need anybody else for that. I'm done. If you and I want to have a confidential conversation, we establish a key, and then we can talk, and we don't need other people to help us. If you want to be anonymous, you need other people to help you, because by yourself, you will not be able to be anonymous. You need them to provide cover. And the other thing about anonymity is that it's very fragile. Anonymity can be broken as soon as you can as soon as you're leaking information that can enable identification at any layer. So this can be your mobile phone that has a radio fingerprint that is recognizable, for example. And I can maybe de-anonymize you by identifying this radio fingerprint. Or I can identify you through your network IP address or other traffic metadata. Or maybe the fingerprint of your device or your browser or your software, the software installed in your computer. Or you have published an anonymous text, maybe I can identify you based on your writing style, or based on some information that I have about blockchain transactions. Depending on the application, you will have different layers. The point is, if in one of these layers you have information leaking that enables identification, all the work that you did at the other layers is kind of lost, because you will not be anonymous anymore. So that's the other key point I want to make, that leakage that enables de-anonymization occurs at multiple layers. So anonymity, you're not done with anonymity when you just have covered one layer. All right. So when we think about private communication, what properties, more specifically, are we thinking about? So first of all, of course, we want the content of communications to be confidential. We want to have other properties such as forward security, such that if, for example, some of the entities are compromised, past communications cannot be, the privacy of past communications is still preserved. And we also want to avoid central points of failure in order to have a distributed trust model that does not rely on centralized parties. Okay. So that's one of the types of properties. We also want to have anonymity. This is the main focus of this talk. Now, anonymity is not just a single property. Anonymity can be defined in many different ways. I'm just giving three main examples of what anonymity can mean. So sender anonymity means that I can send a message to you without you knowing that I sent you the message. So you as the receiver will not know that I sent a message. Receiver anonymity means that you can send a message to me without knowing who I am or where I am located. Or you can reply to me anonymously if I send you an anonymous message. Very often what we want is third-party anonymity. This is a weaker notion. Here, you and I, we know each other, we authenticate each other, we want to sign everything, and we want to be sure of each other's identity, but we don't want any third party to know that we are talking to each other. And this is what is called anonymity towards third party or third party anonymity. Now, I'm simplifying here. There is a recent paper, a very nice paper that was published this summer in the PETS conference that looks into privacy properties that are related to anonymity, and they identified 28 properties. So just to give you a sense of the amount of variables and features that are involved, threat model assumptions, different leakages, and so on. So this is actually much more complex than what I'm saying, but these are kind of very important properties that we often want to achieve. Beyond anonymity, we want messages to be unlinkable. That means that if I send you 2 messages, maybe I want you to not be able to tell that the 2 messages came from the same person. Why is that? Because if you have a system that provides anonymity but not unlinkability, that means that after a while, you will have compile a dossier of all the activity, all the messages that some anonymous subject has been sending. The more information you collect, the more you can reveal about the person, and the more that random identifier that you assign to that anonymous user becomes an actual name, because it has a history attached to it and it has valuable information attached to it. And finally, a very strong property is an observability. So anonymity is not enough, because anonymity does not conceal the amount of traffic that you are sending. It does not conceal when you're online or offline, when you're accessing a service or not, and so on. So an observability is a stronger property that not only conceals who talks to whom, but hides the fact that you're sending a message at all. So to achieve this, we of course need dummy traffic, covered traffic, meaning that you have to be simulating activity even if you're not doing anything. Okay, what about adversaries? So when we want to be anonymous online, what kind of network adversaries are we considering? And in the case of the systems I want to talk about, these are very strong network adversaries. So the capabilities of these adversaries, typically for Mixnets, which is the system I will introduce in a moment, is that this is an adversary that can monitor all the links in the network. So we assume the adversary can monitor all communications in the network. They can compromise a subset of entities in the network, either by injecting their own nodes, which typically is difficult to prevent. This is what is called a Sybil attack, if they really take over by injecting a lot of them. Or maybe they are not able to introduce their own nodes, but they can coerce existing nodes into, or compromise them into leaking their keys or obtaining their keys so that they can, access the internal information of that node. And we typically consider active adversaries that can read, inject, delete, and modify messages. So this is a pretty powerful adversary. What's the objective of this adversary? Mainly, I link a sender and a receiver of a communication. So identify the sender of a received message or the receiver of a sent message, depending on whether you're looking at the input or at the output. And strong limitation we have is that adversaries cannot break crypto primitives and cannot see inside the nodes. They do not control. Okay. So what we're doing instead is a statistical analysis of the metadata that is available at the network to this adversary that is looking at the links, and that is available as well at the corrupted nodes that are able to see some more privileged information. All right, so what kind of systems do we have to achieve these properties against these strong network adversaries? So the original design dates back from the 80s. It's probably older than many people in this room. And is what we can call the Chunyin mix. And this is basically a proxy that performs a shuffle. It takes a set of input messages, shuffles them, and outputs them. These systems typically have a parameter, is a threshold. So for example, if the threshold is 100, it means that the mix will wait until it collects 100 messages. And once it has received the 100th message, it will perform a cryptographic operation, shuffle, and output. So it was proposed to implement anonymous email. And the goal is that even if the adversary is seeing all the inputs and all the outputs, they are not able to correlate which input corresponds to which output. So you want to have a permutation that doesn't leak any information. For that, you need to change the message cryptographically, meaning that the bits should not give any information about what input corresponds to which output. But that's not enough. That's the easy part, actually. The difficult part is that you also have to break timing and order correlations. Because if I know that the first in is the first out, then even if the cryptography is perfect, based on order and timing, I will be able to link inputs to outputs, right? So Chunyin mixes achieve reordering by waiting for these end messages, performing a shuffle, and then sending them forward in a random order. And if you want to distribute trust, you can chain multiple mixes in a cascade. So this is the original design from the 80s. We have other designs have been proposed since. So for example, what about flushing every hour instead of waiting for end messages? In this way, we have a bound on how long it will take a message to be delivered. You can have optional conditions, or you will only send messages if you have more than 20, otherwise the anonymity set is too small, things like that. Pool mixes are an interesting extension. Instead of sending all the messages contained inside the mix, they send only a subset, and they keep the rest inside to be mixed with the new arrivals. So that means that you have a much bigger anonymity set, because once a message goes in, you are not sure when it will go out. Asymptotically, it will go out before the end of time. But you don't know when, and therefore you have a much bigger anonymity set. And a very interesting variant is what is called the stop and go or Poisson mixes that delay each message individually instead of batching. And what they do is that each message is delayed according to a sample drawn from an exponential distribution. And the nice thing about this is that you can actually, the person encoding these delays, which will typically be the sender, can actually predict when the message will be delivered. These mixes provide actually the same kind of anonymity as pool mixes because of the memory-less property of exponential distribution, which means that if you have n messages that came into the mix, no matter at which times they came in, when you see one going out, all of the messages in the mix are equally likely to be the one picked, the one that is coming out first, independently of the order of arrival, okay? Good. So, of course, you don't want to have a single mix. This is a single, a trusted central point. You want to distribute trust to avoid single points of failure. So you want to route messages through multiple mixes. Now, how do you organize these mixes? What's the network topology you're going to choose? So early designs had a free route. That means that you can choose any, let's say, 3 mixes in any order. And this is, for example, more or less how Tor is designed. And on the other end of the scale, you had cascades that are basically, this is the Chaum proposal, where you just chain a set of proxies one after the other. And if you need to increase capacity, then you have to have parallel cascades because you will have a limit on how much an individual connection and computer can, how much throughput it can handle. In intermediate topologies are what we call stratified or layered topologies. They're very interesting because it turns out they actually provide higher anonymity than any of the other designs. Oh, wow, yeah, thank you. They provide higher anonymity while providing very good scalability, in particular compared to cascades. Who selects the routes? Is it the sender of the message, or do each of the intermediaries decide on the next hop? Normally, in mixed networks, as in onion routing, it is the sender that will decide on the full path. That means they have to know the full path. They have to know the full network in order to select this path, which is also a challenge. What about reliable transport? You're sending this message into the mix, and do you know if it arrived or not? Most designs, most existing designs, actually all existing designs except for ours, do not provide reliable transport in the sense that it's a best effort. You have to hope the message is delivered. We actually are able to have acknowledgements using single-use reply blocks that are part of the packet format that we're using that enable sending anonymous replies, and these anonymous replies we're using as acknowledgements so that you can tell back to the sender your message was delivered. And if the acknowledgement is not received, then you know it was not delivered, and therefore you have to resend it. In anonymity systems, there are important trade-offs between latency, anonymity, and bandwidth. Bandwidth in the sense of how much covered traffic you can have, how many users you can handle, anonymity, how much you delay messages, and depending on your priorities, the type of application, the strength of anonymity, you will be in different places on this trade-off. And then what's your degree of centralization? Many of the existing systems, such as Tor, they have centralized components, such as directory authorities that distribute network information. And these are, in our opinion, undesirable if you want to have a truly decentralized system. Again, also, how do you incentivize? You have to have, in anonymity, you cannot do it alone. A lot of people have to work together to achieve anonymity. How do you incentivize these participants? How do you reward them for performing the role? And I will not go into this. This is just to show you the complexity of designing anonymous routing. This is actually part of a survey that we did with Fatemeh Shirazi, who's now at Web3 Foundation, and a survey of anonymous routing protocols. And these are the features that we extracted that you have to actually take into consideration when you want to design an anonymous routing system. So just to show you that there is a lot more that I'm not going into detail here. Okay, so you might be asking, okay, so we know Tor, or we have heard of Tor, so how are mixnets different from Tor? So just to give you the highlights of what is similar and what is different, They are similar in that they are typically source routed. Source routed means that the sender, the creator of the message, is the one who decides on the full route. Okay, this is source routed. Other systems exist that are hop by hop routing, meaning that the sender sends to one entity in the network, and then that entity decides on who the next hop is, and then that one decides on the next. Those systems are vulnerable to root capture attacks, and generally source routed is more desirable. And they're also similar in that we have basically cells or packets that traverse a network with multiple hops, in which each hop is performing a cryptographic transformation of the packet. So now, how are they different? So Tor is connection based. In Tor, you're basically open like a TCP channel end to end. You first establish this channel, this circuit, and then you use this circuit for several minutes to, it's an interactive, bidirectional, low latency channel. Right? Mixed nets are packet based. That means that every packet is routed independently. It means every packet has its own routing information embedded in it. All right, so that's one important difference. Another important difference is that Tor does not add latency because it aims to be as fast as possible, to be usable for web browsing, and therefore, 2 minutes, yeah, close. And does not add latency, and that means that it's vulnerable to end-to-end confirmation attacks. End-to-end confirmation attacks are attacks where you can see the beginning of the connection, so sender to the Tor network, and the end of the connection, Tor network to final destination. If you are able to have these two vantage points, because there is no latency and there is no cover traffic added, you can simply see, okay, a connection started at this time, ended at this time, had so many packets, the packets in the first second were so many, second, and then you can see the same pattern repeating with a small delay at the exit because you didn't reorder packets, you didn't add cover traffic, so you didn't distort this pattern that is in the sequence. While with mixes, we are adding latency, so you cannot perform this easy correlation. You can at best do what is called long-term intersection, which means that statistically, after many, many observations, you start seeing that some recipients are more likely than others to be your target. So it's in that sense, they are a lot stronger. And then another important difference is that Tor aims to be an open system. That means that you can use it to connect to websites, whatever systems that are completely unaware of the existence of Tor, and that makes it very challenging. While in mixes, you typically have a closed system, meaning that the recipient also has software that understands the packet format and can perform a decryption and is in a way integrated or interoperable with the system. Okay? In both systems, you can use dummy traffic. Tor doesn't implement it. Some mixnets don't implement it. We want to use it because that strengthens anonymity and provides an observability. Okay, so the mixnet we're working on, and I'm closing very quickly, is based on Loopix. There is a paper that you can check, uses Poisson mixes, so these mixes that have exponential delays because they have a predictable latency and they produce very large anonymity sets, so we like them because of that. We're using a layered network topology because it's the best topology according to studies that we did already 10 years ago. And we use loops of dummy traffic that create cover traffic in the system, meaning that it's not possible to see if you're doing something at all, you're just sending cover traffic, and that strengthens anonymity and also provides unobservability and deniability properties. We also have reliable transport. We have these ACKs based on these Sphinx single-use reply blocks. These are reply blocks that can be used to send anonymous replies. We use them to send ACKs back and achieve reliable transport. And we have an incentivized network where the mixes are paid for their work. They receive mining rewards for the work they do. And this is for useful work. It's not for useless work, just looking for hashes. And that enables a decentralized architecture. We are now working, we have a very nice design for working on a measurement system that will give us accurate readings that are decentralized and secure of this quality of service, that to make sure that mixes are really indeed not dropping packets. Yeah. You can take a picture or read them.
So we have time for one question.
The last one, come on. I'm really interested in actually your last sentence. What or how can a mixed node prove
in progress.
How does that work?
Yeah, so this is work in progress. What we're doing is basically, the mixes are chosen according to a public algorithm. The router is public, right? So you have a layer of topology, and you will choose first a mix in the first layer, then a mix in the second layer, then one in the third layer. So that's totally routed. And which one within the layer is proportional to the capacity. Okay? Now, how do we make sure that they are not dropping messages? Because this is what we're concerned about. We're concerned about people joining with a mix and then dropping messages and then providing incremental service to users. If this is the case, those people should be kicked out. Right? So the way we do that is that we generate what we call measurement messages. These measurement messages are generated with a VRF, meaning that nobody can tamper with those messages, and we ensure that we have really coverage of all the mixes, all the time slots, all of that is and not like maliciously generated messages. And then, because mixes have to keep reply tags for what we pay a tag, we are piggybacking on that to then enable mixes, once all the measurement messages have been routed through the network, mixes they commit, we use a Merkle commitment, they commit to these methods tree root, and then they will be able to prove that they indeed saw the replay tags that were included in the measurement messages, that they reported those and they committed to those. So then they can prove that this message was passed through them. So then you can reconstruct the full route and see if somebody was dropping or not. And if somebody was dropping, then you keep count on that, and then you need to have some decision-making algorithm to see when you pick up somebody and what tolerances you have for the dropping. It's complicated, I cannot explain it. I'll be around later.
Thank the speaker one more time.